Hello and welcome to this video on finding a matrix that is similar to a given matrix. So in this video, I'm going to define what it means for two square matrices, to be similar. I'll list several properties, true statements about similar matrices, without going into their proofs. If you'd like to see proofs of the properties, look in whatever particular textbook you're working with. That is not the point of this video, right? I'll just state the properties and then I'll demonstrate them through some examples. Then we'll have a couple examples where I'm asked to show that two particular matrices are similar. And then the final set of examples, I'll be given a matrix and then asked to find another matrix that would be considered similar to it. Okay. So this first page, just defining similarity of matrices. So two square matrices, right? Two n by n matrices, or matrices of order n, however you want to say that. Say A and B are similar if an invertible square matrix, same size, right? An invertible n by n matrix called, we'll call M here. It doesn't have to be called M, but whatever you want. Just not A and B. If an invertible matrix M exists such that, now all three of these relations here, all three of these equations are the same relationship, right? Just manipulate it a bit. So you could show either one of these to show that a matrix A and B are similar. So one, you could show that M times B is the same product is equal to A times M. Alright, so you see here I've got the invertible matrix on the outside and then the two matrices that are similar on the inside, right, closest to the equal sign. And do you see what they, hopefully you can see what they mean by similar then here, right? A and B are similar if you find another matrix M, an invertible matrix, such that if I multiply B by M, I get the same result as if I multiply A by M, right? Just in the other order, on the other side. Multiply B by M on the left and A by M on the right, and I get the same result. So A and B must be similar in some way if their product with M is the same. Right. Or, right, just manipulating this, if I just multiplied both sides of this on the left by M inverse, right, because again, M is going to be invertible here, so M inverse would exist. If I multiplied on the left of both sides by M inverse, we'd have B alone, and say that, B equals M inverse times A times M. Alright, so again, another way to say that two matrices are similar is if one matrix is equal to the other matrix multiplied by, an invertible matrix and its inverse on the outside. Same thing here. If I took this equation up here, multiplied on the right of both sides by M inverse, I'm getting the same kind of look, where one matrix A is the other matrix B multiplied on the outsides by an invertible matrix and its inverse. Right. So yeah, so that these are the key, the ones we're going to be using most in the last couple of examples. If I have a matrix A, to form a similar matrix B, you just simply need to take any invertible matrix and multiply on both sides of A by that matrix and its inverse, and you'll get a similar matrix to A. Right. Okay. Now, the next pages, and before we get to some actual examples, are a list of some properties, some true statements about similarity and similar matrices. I've got several of them. And these aren't all the properties out there, but there's some big ones. So now again, I don't have any proofs for these written out. That is not the point of this video. Right? Find them on your own if you wish, or maybe sometime in the future I'll make some videos where we're proving these results. So let A, B, and C be some n by n matrices. Then the following are true. Right? The following statements will be true. So number one, any matrix is similar to itself. Right? Any matrix is similar to itself, and I guess that it would be easy to show that if these were both A instead of A and B, just have M be the identity matrix, the n by n identity matrix. Right? There's an invertible matrix such that IA equals AI. Right? If I is the identity matrix. So any matrix is similar to itself, and this is called the reflexive property, right? When you have a relation, like here the relationship between two matrices is this similarity. If a relationship works for an object and that object itself, that relation is called reflexive. So similarity is reflexive. Any matrix is similar to itself. Number two, if A is similar to B, then B is similar to A. And I've actually already kind of shown this on the previous page. Right? If A is similar to B, that means we have A equals B times some product of, on the outside, matrix, an invertible matrix and its inverse. Well, you see, I just manipulate this and get this then B is similar to A, because I can write B in the same way. All right. So if A is similar to B, then B must be similar in turn to A. This just kind of changing the order, going back and forth like this between two objects, means is called the symmetric property. So you would say that similarity is symmetric, right? If A is similar to B, then B is similar to A. I mean, just switching the order still works. And then third, if A is similar to B and B is similar to C, then you will see that A is going to be similar to C as well. Right? And this is called the transitive property. Right? And you've probably seen this with just equality, right? If A equals B and B equals C, then A equals C. Works also for is less than, right? If A is less than B and B is less than C, then A is less than C, when dealing with real numbers. Here, this similarity also satisfies that same property. And again, I'm not going to write the proof out, but similarity is transitive. If A is similar to B and B is similar to C, then A will be similar to C as well. Sorry, my C there looks like crap because I got jerked around while writing it. I apologize. That is C here. Okay. And then something I'm not going to write, I'm just going to say, since all three of these properties are holding true for similarity, they would say that similarity, the relation of similarity, is an equivalence relation on the set of n by n matrices on R n by n. And therefore we could use similarity to partition the set of n by n matrices into equivalence classes based on similarity, right? None of those words probably mean anything to you. I don't know why I'm saying it. But just know that could be something that comes up in another class on linear algebra, or maybe some advanced linear algebra in the future. All right, but not today. All right, so we have reflexive, symmetric, and transitive properties holding. And then finally, now this one has like 4 parts to it, right? And again, these aren't every property in the world related to similar matrices, right? Just some important ones I feel you should know. If A is similar to B, then the following four statements are true. All right, so these are all true statements about similar matrices. The determinant of A will be equal to the determinant of B. All right, so similar matrices have the same determinant. Right? Now be careful. The converse is not true. Just because two matrices have the same determinant doesn't mean they'll be similar, right? And that's easy to see. If you have a 2 by 2 matrix with a determinant of 3 and a 3 by 3 matrix with a determinant of 3, a 2 by 2 and a 3 by 3 aren't going to be similar because they don't have the same size. All right, so just because two matrices have the same determinant doesn't mean they'll be similar. And it also works out for some matrices that are also the same size, like the 0 matrix. The 0 matrix can only be similar to the 0 matrix. And it has a determinant of 0. And there are plenty of other 2 by 2 matrices out there with a determinant of 0 that would not be similar to the 0 matrix. All right, so it only goes in this one direction. If the matrices are similar, then they have the same determinant, but not the other way around. Okay, you can't guarantee that. All right, number 2. If A is similar to B, right, if A and B are similar, then A is invertible if and only if B is invertible. So they're either both invertible or they're both not invertible. Right? They're either both non-singular or they're both singular, right, if they're similar. Okay, number 3. If A and B are similar, then their ranks will be equal. The rank of A will be equal to the rank of B. Right? I'm assuming you've seen rank, right, in previous videos of mine or previous lessons. Remember, the rank of a matrix was the dimension of the column space or the dimension of the row space, right? Those were the same number of that matrix. Also, since they're similar, they have the same size, they're both square, that means they have the same number of columns. You could also state then that A and B would have the same nullity, if they have the same rank. And remember, the nullity of a matrix was the dimension of the null space of that matrix. But I've only written the rank here. All right. And then finally, the last of the properties I'm mentioning here today. If A and B are similar, right, if they are similar, then the spectrum of A will be equal to the spectrum of B. Now remember, the spectrum, this little lambda of A, lambda of B, remember the spectrum of a matrix was the set of all the eigenvalues of that matrix. And again, I'm assuming here you know how to find eigenvalues at this point. So the eigenvalues of A will be the same as the eigenvalues of B, if A and B are similar. All right. Wonderful. Okay. So now that I have these properties out, and I'll bring these last 4 back. All right, the 4 part 1, 4 part 2, 4 part 3, and 4 part 4. I will bring these 4 statements back into play when we take a look at some examples here coming up. All right, so in my first few examples, I'm given the following directions, following instruction. So show that matrices A and B are similar using invertible matrix M. All right, so I want to show that these two are similar. So remember, you can do 3 things. One of these things. You don't have to do all 3. We just need to show that either M times A equals B times M. Right, just show that A times M on one side on the left equals B times M on the right. And again, you could switch these if you wanted to, but show that when I multiply these matrices by M on different sides, I get the same result. All right. So let's do that. I'll do that first. All right, so now again, notice now that M is invertible, right? The determinant of M here is non-zero. In fact, the determinant of just to double check, the determinant of this matrix would be 1, right? 1 minus 1, which is not 0, so it's invertible. It satisfies the definition. I need an invertible matrix such that this happens. All right, so M times A. That's the matrix M times matrix A. And what am I getting? All right, I'll multiply the 2 by 2 times a 2 by 2 will be a 2 by 2. 1, 1 with 2, negative 1. Again, you know how to, hopefully you know how to do matrix multiplication by now. All right, this is 2 minus 1, or 1. And then first row, second column, negative 2 plus 3, 1 again. Then second row, first column would be negative 1, 0 plus negative 1. And then second row, second column would be 3. All right, and then let's take a look at the other side, B times M. I multiply A by M on the left, and multiply B by M on the right, and see if we get the same product. And if we do, that means that A and B are similar. So B is 3, negative 1, negative 2, 2. Multiply by this invertible matrix M here. And now it's a 2 by 2 times a 2 by 2, and hopefully I get the same thing. First row, first column would be 3. 3 plus 0. Okay. Did I? Okay. Okay. And I'm noticing that when I do B times M here, looks like they're not similar in this way. But I'll have to remember, order for multiplication matters, right? So they're similar in the other way using this matrix M. Let me show you, right? So like when I multiply these matrices, I'm getting 3 here. It's like, ooh, these aren't equal. So they're not similar in this way, right? In these orders. So that's not good. Then I try the other order, right? Or try M times B and see if that's equal to A times M. Right? Because you see, when I did it up here, I multiplied by A by M on the left and B by M on the right, and saw, ooh, they're not similar in that fashion. Try it the other way around. Try multiplying, instead of B by M on the right, try multiplying B by M on the left. And instead of A by M on the left, I'm doing A by M on the right. And if this is true, if either one of these is true, you have similar matrices. All right, so sorry about this little stuff here, right? But it's good to check, right? Doesn't hurt. So again, ignoring, just going to kind of, this isn't equal, skipping this work here. And now we're coming down, checking this, right? Is M times B is that equal to A times M, right? All right, so what's M times B? That's 1, 0, 1, 1 times B is 3, negative 1, negative 2, 2. And when I multiply these matrices, I get first row, first column would be 2, then 0 for the first row, second column, then negative 1 for the second row, first column, and then 2 for the second row, second column. Okay, and let's see if this is equal to A times M. A is 2, negative 2, negative 1, 3 times M, 1, 0, 1, 1. And now we're getting it. See, first row, first column would be 2, so looking better already. First row, second column would be 0. Second row, first column would be negative 1, and second row, second column would be negative 1 plus 3 or positive 2, and hey, that's a lot better. Right. So we have M times B, so in this order it works. this order it didn't. But if it works in one of these orders, you do have similar matrices, right? If you can find an invertible matrix called M such that this is a true statement or this is a true statement, right? That where you multiply one matrix on the left by M and the other matrix on the right by M and get the same result, then the matrices are similar. Right, so since MB is equal to AM here for this invertible matrix M, we can say that A and B are similar. All right, and since MB is equal to AM, right, another thing I could have shown. Another thing I could have shown was that, again, since since we see that, since MB is equal to AM, we could have also tried to show that B is equal to M inverse times A times M, right? Or B mam, right? Where M inverse, show this. And very often you'll see people just start off with this to try to just show that two matrices are similar. Matrix B and A are similar. Let's see. Well, I would need to find M inverse first, right? So now I already told you the determinant of this 2 by 2 matrix was 1. Right, so what is M inverse? Remember, it's just the reciprocal of the determinant times the adjoint matrix, which for a 2 by 2 matrix is very simple. You just switch these main diagonals, which are still 1 and 1, and you have the opposites of these, so negative 1 and 0. There's M inverse. And let's see if this is true, right? Because if this is true, then this is true, and they're similar, right? Matrices A and B are similar. So what's M inverse times A times M? So M inverse I have there, right, in this order. So 1, 0, negative 1, 1, times A, 2, negative 2, negative 1, 3, times M, times the 1, 0, 1, 1. Right? And hopefully this is equal to B. Right? Now remember, matrix multiplication is associative, so if you're multiplying 3, it doesn't matter what order, so I'll just do these two first, let's say. So we have 1, negative 1, 0, 1. Multiplying these two. Well, I did AM on the earlier page, right? A times M is this matrix here, 2, 0, negative 1, 2. And multiplying these two matrices gives me another 2 by 2, where first row, first column is 2, plus 1 is 3, which looks like, hey, so far so good. All right, that's the first row, first column of B. And then first row, second column would be negative 2. Hey, that's the first row, second column of B. And then second row, first column would be negative 1. Second row, second column would be 2. Hey, look at that. That is indeed B. So I have this being true, right? B equals M inverse times A times M. And if that's true, then we can go back and say, hey, then M times B must be equal to A times M. If I multiply these two matrices by this invertible matrix M on either side, one on the left, one on the right, I'm getting the same product. That means A and B are similar. Right. A third thing we could have shown, since MB equals AM here, we could also try to show that A equals M times B times M inverse. And I'll leave that to you. All right, that should work though. If you take this times this, this M times B times M inverse, your final result should be A, right? If A and B truly are similar. Okay. So next example. Oh, you know what? I also wanted to bring back these statements. Right. Okay, since A and B are similar, remember these statements here, right? Now we've seen that A and B are similar now, right? Because we found an invertible matrix M, such that MB equals AM. or this might be true as well. MA equals BM. If either one of these, as I said earlier, if either one of these is true, you have similarity. So since A and B are similar, their determinants should be the same. Let's verify that. We've shown that A and B are similar. Right. So let's look at their determinants, right? What's the determinant of A? Well, it's only 2 by 2. That'd be 6 minus 2, that's 4. And what's the determinant of B? 6 minus 2 again, also 4. Right? They're the same. Look at that. That's going to happen for any similar matrices. They're going to have the same determinant. And like I said earlier, be careful. Just because two matrices have the same determinant doesn't mean they're similar. Right? And I mentioned that with like the zero matrix or even the identity matrix. The identity matrix would only be similar to itself, and it has a determinant of 1. And there are plenty of other matrices out there with a determinant of 1 that would not be similar to the identity matrix. Remember this statement too. A is invertible if and only if B is invertible. Well, that means they're both invertible or they're both non-invertible. Well, that comes from the fact that the determinants are the same, right? If both the determinants are not 0, which these are here, then they're both invertible, right? So A and B are both invertible. If the determinants are both 0, then they're both not invertible, right? Here we have A and B are both invertible. Their ranks must be the same, right? Now, remember the rank is the number of independent column vectors of the matrix, or the basis, or the dimension of the column space or the row space. Now there's only 2 rows here, and you see these 2 there's only 2 columns, and do you see these 2 columns aren't scalar multiples of one another? So the rank is 2. There are 2 independent column vectors, right? Again, since it's invertible, when you put it in reduced echelon form, it should be row equivalent to the identity matrix, right? So each column in echelon form would be a pivot column. There are 2 of them. Same thing for here, right? The rank of B, right? Each of these columns, again, are not scalar multiples. These columns are linearly independent, so the rank is 2 again. They have the same rank. They would both have the same nullity of 0. I remember the rank plus nullity equals the number of columns. All right, and then their spectra will be equal. All right, the spectrum of A will be equal to the spectrum of B. I'm actually, just to save some time here, I'm going to leave that to you to figure out. Find the eigenvalues of A and find the eigenvalues of B separately. Right. And you'll see that the eigenvalues of A will be exactly the same as the eigenvalues of B, I promise you. All right. Just to save some time here. Again, because finding the eigenvalues you've seen in previous videos can be a bit time consuming. All right. Okay. So now, next example. I'm asked to show that A and B are similar using this invertible matrix M. Right? They're telling me this is invertible. So, is A similar to B? Right? That's the question being asked here. Or show that they are. So again, you can, so the question, that's the same as this question, is either M times A equal to B times M, or M times B equal to A times M. Alright. So I'm going to check that one this time, because again, I think that I pulled these examples from a textbook where they were using this formula, instead of this one. So I'm going to check this one this time straight up. So let's try it out. All right. So yeah, remember, A and B are similar if you can find an invertible matrix such that one of these is true, right? Such that you multiply both matrices, one matrix on the left by it, one matrix on the right by it, and you get the same result. All right, so what's MB here? MB is, there's M times B. Now the nice thing about B is it's a diagonal matrix, right? The only non-zero entries are on the main diagonal, so it should make multiplying pretty simple. All right, so M times B, 3 by 3 times a 3 by 3 is a 3 by 3, and I'm getting for the this 4, 4, then -2, and 0 for the first row, and second row and the stuff, 4, and +2, and then 0, 0 again. Really what you're going to notice is you're getting 4 times the first column, -2 times that column, and -2 times that column as your output. But let's just keep going here. So you got 4, so 0 for the third row first column, 0 for the third row second column, and then -2 for the third row third column. Again, multiplying by a diagonal matrix, very simple. Just take the first diagonal entry, multiply that by the first column, second diagonal entry by the second column, third diagonal entry by the third column, and you see I'm getting this matrix here. All right. Then check the other way around. Check A times M, right? Multiplying B by M on the left, A by M on the right, and see if I get the same product. All right, so A 1 3 0 3 1 0 0 0 -2. Multiply by this invertible matrix M here, 1 1 0 first row. Okay, and yeah, so this will be a 3 by 3. So we have what, for 1 plus 3 plus 0, so 4. Then 1 plus -3 plus 0, -2, and it should be the same as this, right? And then 0 0 0. And then 3 plus 1, 3 minus 1, bunch of zeros, and then zeros, zeros, and -2. And look, they are the same. M times B equals A times M. When I multiply one matrix on the left by this invertible matrix, I get the same result as when I multiply the other matrix on the right by the same invertible matrix. So we have MB is equal to AM, right, for this invertible matrix M. Therefore, A is similar to B. And don't forget, there were other things. Now that I see this, there's other things we can show. All right, this would mean that B would be equal to M inverse times A times M, and I leave that to you to check right now. Okay, you would just find the inverse of this 3 by 3 matrix, put it here, times A times M, you'd get B back, or again, same equation, manipulating it, we'd see that A would have to be equal to M times B times M inverse. Right? But both of these should be true since we've shown that these are similar in this fashion, that MB equals AM. All right, and since they are similar, all right, since A and B are similar, the following statements should hold. Right? Their determinants should be the same. Now the determinant of B is a simple one, right? Because it's a diagonal matrix, right? And remember, for a diagonal matrix, or even just triangular matrices, upper triangular, lower triangular, the determinant was simply the product of the diagonal entries. 4 times -2 times -2, that'd be positive 16. This would also have a determinant of positive 16. I would know this because I've already shown that they are similar. And if two matrices are similar, they are going to have the same determinant, right? Just not the other way around. Right? And this one wouldn't be too bad to check either. Just do cofactor expansion down the third row or down the third column. You'd have -2 times this determinant, which would be -8, and then that's positive 16. And since both determinants are the same and they're not 0, they're both invertible, right? Since they're both invertible, they'd have ranks of 3, right? All 3 column vectors would be independent, all 3 row vectors would be independent. They both have ranks of 3. Their ranks are the same. And their spectra would be the same. Now this one's real easy. The spectrum, remember the spectrum of a diagonal matrix, or just any triangular matrix really, right? Which a diagonal matrix is both upper and lower triangular, is just those diagonal entries, 4 and -2. All right, 4 and -2 are the eigenvalues of B. And since I know that these are similar, the spectrum of A would be the same. All right, also have A would also have eigenvalues of 4 and -2. All right. Great. All right. So those examples there. Now I was given a matrix A, a matrix B, and asked to show that they were similar using some invertible matrix M. Now, in the examples I have for the rest of the video, I'm going to be given a matrix A and asked to find a matrix that's similar to it. All right, using some matrix M. All right. And you could really, and the M, right? The M can be any invertible matrix. All right. Any invertible matrix to find a similar matrix. So here, find a matrix that's similar to A using invertible matrix M. Again, this could be any, I don't have to use just this M to find a similar matrix to A. I can use any invertible matrix I wish. And I'll show you on this same page here. All right. So what we're trying to do is we're trying to find a matrix B such that a same size, a 2 by 2 matrix, right? Such that M times B equals A times M. All right. Where I multiply, or M times A equals B times M. Okay. Either way, they'd be similar. Right? Well, I don't know what B is, right? So to find B, I need to take, multiply both sides by M inverse here. I need to take M inverse times A times M. And this matrix B will be a matrix that is similar to A. Right. So let's find M inverse. Right now, the determinant of M. Again, I picked a nice one here. This has a determinant of 16 minus 15, just a determinant of 1. So M inverse is very simple. Right. It's just the reciprocal of 1, so 1. Times the adjoint matrix for this, which would just be switching the main diagonals and then taking the opposite of those other entries. So this 2 by 2 matrix with the columns 2, -5, and -3, 8 would be the inverse of M. And you can double check that by multiplying these, and you should get the identity matrix. Okay. So this matrix B I'm looking for then is M inverse 2, -3, -5, and 8 multiplied by A, right, the matrix I was given, negative 3, 1, 5, 2, times M, right, M, the one given there, 8, 3, 5, 2. All right, so I multiply these. Now I'll do these two first. So here's M inverse, right, and then I take A times M. So I'm getting, negative 24 plus 5 is negative 19. Then negative 9 plus 2, negative 7. Then 40 plus 10, 50. 15 plus 4, 19. Right, and then multiplying those two, we're getting this matrix B that would be considered similar to matrix A. So we get negative 38, minus 150, so minus 188. Then negative 14, minus 57. Negative 14, minus 57, I mean negative 71, right, 14, 57, 71, right. Then second row, right, we have let's see, 90, 95, right, positive 95 plus 400, so 495. And then 35 plus, what is that, 80 and 72, that's 152. So 152 plus 35, 187. 152 plus 35. Okay, this matrix is similar to matrix A, right? Because they're, if you took M times B, you would get the same thing as A times M, right? And you can double check that for yourself. But like I said, that's not the only similar matrix to A, right? There are every matrix except for the zero matrix and the identity matrix. Every matrix has infinitely many matrices that are similar to it. Just take this M here, make this M any invertible matrix you wish. So I could have done the same thing, right? But instead of using this M, I use another M, that's invertible. So how about just, one, again, I'm just picking ones with determinants of 1, but 1, 1, 0, 1 there, right? And, just not the identity matrix. Because remember, a matrix is definitely similar to itself. Then I think we had this one up earlier. M inverse would simply be this, right? And then I take M inverse times A times M, and this gives me a matrix B that would be similar to A, right? Because if it would be MB equals AM. So we have 1, negative 1, 0, 1, M inverse times A times negative 3, 1, 5, 2 times M times the 1, again, not this M, but this M, 1, 1, 0, 1. And I keep M inverse here, multiply these two. That'd be negative 3, and negative 3 plus 1, negative 2, and 5 plus 0, 5, and then 5 plus 2, 7, and then multiplying these, getting negative 3 minus 5, negative 8, negative 2 minus 7, negative 9, and then 5, 7. Right? And here is another matrix. Right? here's another matrix that is similar to matrix A that was given up there. Right. And like I said, you could do this all day long. You can make up all sorts of examples. Just replace this M here with any 2 by 2, any invertible matrix you can think of. So any matrix where the first column and second, where the determinant's not 0, or where the first column and second column aren't scalar multiples. And let's see. Remember, if these, so this matrix with the negative 3, 5, 1, 2, this matrix with these crazy numbers, right, and this matrix are all similar, right, by the transitive property. Because remember, this matrix is similar to A, and A is similar to this, so this must be similar to this as well, right? There was that transitive property, and all three of these are similar, right? So their determinants should all be the same, right? That was this statement here, right? Their determinants should all be equal. Their ranks should be equal. They should all be either all invertible or all not invertible. So let's see, what's the determinant of this matrix here? It's negative 6, minus 5. It's negative 11. That should be the determinant of this matrix as well. All right, so I'm going to go to a calculator for this one. I'm just doing, negative 188. All right, sorry, my calculator's a little. I'm going to pause this while I type this in. All right, you see on the calculator here, I typed in the determinant of this 2 by 2 matrix here, negative 188 times 187 minus negative 71 times 495. And you see it comes back negative 11 on the screen there. And the determinant of this other matrix I found that was also similar, right? That's negative 56 plus 45. That's negative 11 again, right? So all similar matrices, right, have the same determinants. They're all invertible, right, because all of them have the same determinant. That's not 0. They all have the same rank, which would be 2. And they all have the same spectrum, right? They all have the same eigenvalues. And again, I would leave that to you if you want, but find the eigenvalues of A. Those would be the same as the eigenvalues of this crazy matrix with these big numbers. Same as the eigenvalues of this matrix. All right. Again, it's very easy to find a matrix that's similar to a given matrix. All right. So if you're given a matrix and asked to find a similar matrix, just find any invertible matrix of that size and multiply the given matrix on both sides by the matrix itself and its inverse. Right. And you'll have a similar matrix to the matrix you were given. Right. Okay. So I've got just one more example of this. Well, no, I've got two more. One more 2 by 2, because we haven't seen one where the determinant's 0 yet, like here. What's the determinant of A, right? It's 0, 6 minus 6. I'll write that right here. So it is not invertible. So that means any matrix similar to it should also not be invertible and have a determinant of 0. And you can probably see that it would also have a rank of 1. Right, because if I were to put this into reduced echelon form, I'd have the row 1, 3 moved up top, and then I could make the top row 0, 0 moved to the bottom. Because I just take negative 2 times row 2 plus row 1 to make that a 0 row. So it's only going to have, when you put it in the echelon form, only going to have a 1 pivot column, right? So the dimension of the column space for A is just 1. Now over here again, this could be, if I say here's a matrix A, find a matrix B that is similar to it. Right. we're just trying to find a matrix B, matrix B, B in there, such that, M times B equals A times M for some, right, for some invertible matrix M. Right, so again, you can pick any matrix, any invertible matrix you wish. Now here I have this invertible matrix, with 4, 7, 3, -5. So in order to find this similar matrix, a matrix that's similar to A, I'm doing the same thing where I take my invertible matrix M, I multiply A on either side by the matrix and its inverse, right? So, and again, if I want this to be true, if I want MB times AM, MB to be equal to AM, then B must be equal to M inverse times A times M, right? So we could find M inverse pretty easily, right? What's the determinant of M up here? I think this one's -1, right? 20 minus 21. So then M inverse is -1 times that matrix where I switch these and make these opposites, but then I'm going to multiply by -1. So again, it'd be very easy to check that this is the inverse here of M. And you can check by multiplying them. Multiply these and you should get the identity matrix back in either order. So let's do it. Let's multiply, M inverse times A times M. Let's see what we get. All right, so again, I'm going to do these two first. All right, so first row, first column, we have 8 plus 42, that's 50. Then 6 plus 30, right, 36. Then 4 plus 21, 25. And then 3 plus 15, 18. All right, then multiplying these guys, we have -250 plus 75 be -175, and then let's see, that's -180, which is like -10 times 18, plus 3 times 18 be -7 times 18, 70 plus 56, -126. Right. Then 350 minus 100, so 250, and 210 plus 42, 252. Oh, actually, you know what? That's just 2 times 18. So that's 14 times 18 minus 4 times 18. That'd be 10 times 18. That'd be 180. And this matrix here is similar, it should be, to matrix A. And a way you can really double check this is, multiply this matrix on the left by M, multiply A on the right by M, and they should give you the same result. Right. And if you'd like to just, this doesn't prove anything, but if these two are truly similar, they'll have the same determinant. So let's see if I get the same determinant here. All right, so back, again, big numbers, I know, sorry. Back to the calculator. All right, so I'm putting in the determinant of this matrix B down here should be 0, right? The determinant of A was 0. This is similar, so it should have the same determinant. So -175 times 180 and then, well, plus, because I have minus a negative there, so plus 126. Didn't register the 1. All right, so 126 times 250. I probably should have done this mentally. It would have been faster. Sorry. And look at that. It is indeed 0. Right? And that should be the case. And the rank, it's determinant 0, so it's, not invertible, just like A. Its rank would be 1, just like A. And the eigenvalues would be the same. Right? The eigenvalues of A would be the same as the eigenvalues of B. All right. Okay. So again, very, very simple. If you're given a matrix and asked to find a similar matrix, that just means you're trying to find another matrix B, such that this is true. For any, you can find, as long as you find an invertible matrix M, that makes this true. Right? So the choice of M is up to you. You pick any invertible matrix you want. I just happen to pick this one, right, to make some other similar matrices to matrix A. All right, so I've got one more here. All right, one more. This time with a 3x3. This time I'll just punch things in the calculator. It's been a little slow, but I'll pause the recording to enter some things. So again, here's matrix A. And I'm asked to use this matrix. Now again, this is an invertible matrix. It's an upper triangular matrix, right? The determinant of M over here is 1. It's invertible, right? The determinant's not 0. And I'm asked to use this to find some matrix that's similar to matrix A. All right, so I want to find B. Again, I'm trying to find some matrix B such that M times B equals A times M. You could also use the other way around, right? You could also use M times A equals B times M. A and B would still be considered similar here, right? So I can get 2 similar matrices just from these, right? From here, B equals M inverse times A times M. This would be one matrix that's similar. And let me call this one B prime just because it'll be different. From this one, I'd get B prime equals, M times A times M inverse. And both B and B prime will be similar to matrix A. All right, so I'm going to go to the calculator. I'm just going to pause this recording for a bit and enter these matrices and get their inverses and stuff. All right. So I'll be right back. Okay, so taking the time to enter these matrices. Now matrix A, I called matrix A in the calculator. Matrix M, there is no M choice in the calculator, so I just called that matrix D in the calculator. Okay, so when you see matrix D, that's matrix M. All right, so let's calculate this first one, using this equation here, where 2 matrices are similar. If you multiply one on the left by an invertible matrix and the other on the right by that same invertible matrix, you get the same result. Let's take M inverse times A times M. All right, so in this case, D inverse. So again, I've entered these matrices here. Matrix D is matrix M. So D inverse, right, so a little -1, x to the -1 button there, times matrix A. So back to the matrix menu. Matrix A is this 2, 1, 4, 1, 0, 3, 3, 0, 8 matrix, times, and then matrix D is again matrix M. All right, so the matrix with 1, 2, 3, 0, 1, 4, 0, 0, 1, I called matrix D in the calculator. All right. So I've taken its sweet time. Okay. Okay, so there's D inverse times A times D gives me this matrix here. All right. So B equals 15, 31, 87, negative 11, negative 22, negative 62, 3, 6, 17. All right, this should be similar to matrix A. All right, and if they are similar, they should have the same determinant. All right, well, let's check. Now, I purposely set up again matrix A up here so it was a nice, easy one to find the determinant for by hand. I could just do cofactor expansion down the second column here. So it'd be 1 times its cofactor, which, since that's in an odd position, right, first row, second column, 1 plus 2 is 3, that's odd. Since that's in an odd position, its cofactor will just be the opposite of the minor. The minor would be the determinant 8 minus 9, or negative 1. The opposite of that is 1. 1 times 1. The determinant of that matrix is 1. And again, if that was too fast for you, do it by hand on your own. So the determinant of this matrix should also be 1. Let's see, I'll just use the calculator for this. Go back to the matrix menu, over to math, and take the DET there, determinant of the previous answer, because that previous answer is the matrix in question, this matrix B I have written here. Right. So second, and then above the minus sign has the previous answer. And look at that, it's 1. All right, so that means that there's a good chance they're similar. I mean, they should be similar because I found this relationship here. All right, but the same thing should be over here. All right, this should be another similar matrix. So again, I call this B prime. All right, B prime is just M times A times M inverse. Again, real simple. I'll say it again. If you're given a matrix, a square matrix, and asked to find some similar matrix, right, some matrix that's similar to it, just take any matrix that's invertible of the same size and multiply your matrix by that matrix on one side and the inverse on the other. So I did that here with the matrix on the right, the inverse on the left. I did it here with the matrix on the left, the inverse on the right. Either way, you're getting a similar matrix to matrix A. All right, so this time I have, in my calculator, it's D times A times D inverse. All right, so bear with me again here. So I'm calculating matrix. I could have just said the number 4, couldn't I? All right, matrix D times matrix A times, and then D inverse. With a little minus 1 there. All right. And this time we're getting this matrix. All right, so the first column 13, 13, 3. Second column negative 25, negative 26, and negative 6. And third column 95, 123. And this should be also similar. This is also similar to A. Right. This B prime that I'm calling here. And if it's similar to A, it should have the same determinant. All right, this matrix should also have a determinant of 1. Let's see that that's happening. So matrix, math menu, and then the determinant of the previous answer, right, that matrix. So second answer. And this should also be 1. And it is. Fantastic. Right. But yeah, so again, very simple procedure to find a similar matrix to a given matrix. Take that matrix, find a matrix of the same size that's invertible, right, which again should be easy to make up. You can make up, I just made up a nice triangular matrix, right, upper triangular, because the determinants of those are easy to find, right? Determinant, I just made sure that the diagonal entries none of them were 0. And there's an invertible matrix, and then you multiply this matrix on one side by the matrix and on the other side by the inverse of that matrix. Right? By one side by m, the other side by m inverse, or on the left side by m, on the right side by m inverse. And either way, you're getting an output, you're getting a result that's a similar matrix to the matrix A that was given. Right? Wonderful. Because they satisfy this equation here where you have the invertible matrix on the outside and then the two matrices that are similar close to the equal sign on the inside, right? Same thing here. The invertible matrix on the outsides and then those two matrices that are similar on the inside. Right? If you find matrices that satisfy either of those, they are similar. Wonderful. And they should have all this matrix, right? All have the same rank, right? They're all invertible, so they'll have a rank of 3. They'll also have the same eigenvalues, right? So this matrix, A, B, and B prime here, all have the same eigenvalues as well, and you can double check that on your own. And again, don't be confused though. These aren't the only two similar matrices to matrix A. These are the two I found using that matrix, this matrix M. You could pick another matrix M, right, some other invertible matrix, and do the same procedure and find 2 more similar matrices to matrix A. Right? You can go on forever. All right. So hopefully the concept of similar matrices, what does it mean for 2 matrices to be similar? Hopefully that makes sense by now. And hope you enjoy practicing problems where you're given a matrix and then asked to find similar matrices that are similar to it. Right. And thank you very much for watching.